Hello everybody, my name is Yves Parès and I'm going to present to you today the work that we've been doing together with Jean-Philippe Bernardi and Richard Eisenberg, which is placed in the context of structuring applications in data science. So, as I mentioned, in data science there is a very common pattern to structure application which is called a workflow. So I will first describe what I mean by a workflow of tasks. Then I will show you a bit of how to represent the units of computations that a task may want to perform in the shape of abstract effects. Then I will present the main contribution of our work, which is the Kernmantle framework and library. I will give you some small example in the machine learning context, and then I will show you how it is implemented using the existing common Haskell abstractions. So first of all, what is a task and what is a workflow? So as I mentioned, it's a paradigm that's really predominant in the data science field to structure applications. So very simply, a workflow is a directed, often acyclic graph of tasks, each task performing some effects like pulling some data, training some model, asking some model to classify, to predict some class based on some input data, and so on. This advantages of this paradigm is that, well, when this when this structure is made static, when we know which tasks are going to be performed in the pipeline or in the workflow in advance, we can use that structure to perform some optimizations. So not static optimizations when the program is compiled, but optimizations like, for instance, deciding when the workflow should run over a cluster, deciding which nodes should take care of which tasks, that sort of stuff. We can run in advance some checks, check if resources are present, if network connections are okay, that sort of stuff. And it turns out that in Haskell we already have quite some nice abstractions to represent what tasks and what workflows should be. Notable abstractions are category, perfunctor, and arrow. And they have the nice property of homogeneity. It means that one task and one workflow will just be the same type, because when you compose two tasks together, you get the same type. And so a full workflow will, by the magic of this property, be another task ready to be reused in a bigger workflow. So this gives us, as it is customary with these abstractions in Haskell, composability and reusability. Also, it enables some separation of concerns quite easily. So this will be brought by the abstract effects, which I'm going to talk right now. So this little block of code describes two effects, one that just describes what it is to log some block of text. So here the A represents the input of the effect and the B represents the output. This effect is just a data constructor, it's fully abstract. We just use a GADT here in order to specify that in the case of that operation, the input should be some text and the output is just unit. And the second effect is how to perform some inputs and outputs on files. So read a file is parameterized by a file path. I will detail a bit later why I put the file path here and not here in the input of the effect. But for now, read is just parameterized by a file path that takes nothing else as an input and returns a text as an output. And write takes similarly a file path. It takes the content to write into that file and returns nothing. In order to execute these effects, we need to perform some I/O, so we need to interpret them, to handle them into some core type, which will be here just some A to IOB function. People who know arrows already can recognize the Kleisli type here. So we have two interpreter functions, two handlers, one that will turn log into this core type and one that will turn file I/O into this same core type. And we can regroup these handlers into some H-list here. So each of these effects will be given a name, log and file I/O. They're given a name and we just regroup the handlers together in some H-list. What we are missing right now is a way to structure these effects, to chain them together into tasks and into workflows. And this is what our main contribution, which is the rope type, is about. So I will not dwell right now, I will detail a bit more, it will become clearer what this type is about in the rest of my presentation, but just know that the core type is here present, so the destination of the interpretation, the common type in which every effect will be interpreted is present here, and we regroup all the different effects into something that we call a mantle. So a mantle is a collection of named effects. A named effect, we call that a strand, and the core is the interpretation target of all handlers. So for instance, using the two effects I previously defined, I can just ask for one task to read some file. So I trigger a read effect saying that I want to read from some file named input.txt, and then the output of that effect is directly fed to another effect, which is just I want to log the content of that file. So it's a very trivial two-task pipeline that triggers two different effects. And the type signature here mentions that we want these strands to be present into the core that we manipulate. Note that we do not care about the core, we only require that it is a category. Why? Because we need some operator in order to be able to change these effects. So this operator is just the reversed function application. It's just composing two tasks together, provided the output of the first is the same type that the input of the second. So why is it named Kernmantle Rope? It's called a rope because of an analogy with Kernmantle ropes in rock climbing. So you can see here that it's a rope constituted of a mantle here, which is made of different strands, and we view each effect as being one strand in that mantle. And this mantle surrounds a core, which is also some kind of rope, which is also some kind of effect, but it really is what makes the rope sturdy. It's really so in our analogy, it's really it's really the type in which the application will run. So our main contribution is Kernmantle, and the main application of a Kernmantle is to be used in applications where we want the runtime to be split in two phases. First, we have the configuration time phase. These are all the computations that should run before the, strictly speaking, pipeline runs, between the application logic runs. So any kind of checkings of preliminary optimizations, of diagnostics, anything that could be verified before actual computation that might be time-consuming are performed should be performed right at the beginning of the program. And then we have the process time, which is actually when the real application's logic is running, when the logic that has been developed by the data scientist, by the data engineer is being executed. So to do that, we have one core data type, which I presented, which we call rope, which is about weaving together different abstract named effects. When a developer or a data scientist writes a pipeline, he does not have to care about this configuration time or process time. He just writes these effects, he just writes the effects he or she wants to trigger. And then the interpretation of these effects is really where the developer which chooses how to interpret these effects, depending on the context, depending on the deployment environment and everything, can choose what phase should be targeted, either one or both of the phases. So the key points is that, much like with any other effect library, we can target different environments by just swapping the handlers we use. For instance, we could have a set of handlers to use our pipeline in testing mode and another in a production environment. And the workflow's logic, as I said, is kept fully abstract. Data scientist does not have to care about what is really needed to have the effect run safely and robustly. We will show that it integrates nicely with existing Haskell abstractions, like Applicatives, functors, and Monads. And also one of the advantages is that it allows us to develop separate libraries of effects, each one with their own effects and effect handlers, and we can then nicely glue them together into a uniform application. So I will now give a more featureful but still quite simple example in machine learning. So this pipeline, which I show here, is made of only 3 tasks, triggering 2 different kinds of effects. Our first effect is just get image. So it's using the arrow notation here. So for the people not used to this notation, it just really means that I'm using 3 commands. The first one is get image. The second one is predict the class, classify this image using some model, and the other one is classify this same image using another model. So here I'm just using the same syntax you saw before to trigger some effects. The first one to get the image, and the two other ones to run some prediction effect that will be based on some model. So once I run this code fragment, what you will see is that first it is downloading the models. So first I've commented the use of the second model, because this model doesn't exist and I want first to show you something that works. So it says that it downloads the model first and then it starts the pipeline. And then it finishes its prediction, which it outputs into some separate file. And if now I rebuild the code by uncommenting the use of the second model, the one I called rubbish, then you can see that it tries to download it first. It does not even say it's starting the pipeline, but it fails here. So we have early failure in that occasion. But yet the code that we wrote does not at all mention any kind of downloading, any kind of check or anything. It looks like imperative code. It looks like instructions laid out one after another. But yet Kernmantle is able to extract out of that code the fact that we will need that model, which exists, and that we will need that second model which doesn't exist, and it can check that they exist before actual computation will run. So in order to give now some insight about how that is implemented, first a quick recap for the people not knowledgeable about arrows. What is an arrow? Well, it's a generalization, sorry, of a function. So in a nutshell, it's some type that satisfies some laws, but most importantly, that has some input and some output, so called here X for the input and Y for the output. In Haskell, the treatment of arrows is sometimes a bit daunting due to the amount of type classes that exist for arrows. So at the root of it, you have the category that deals with composing two tasks, two computations together, and giving you an identity computation that does nothing. Then you've got arrow that deals with parallel computations, and then you've got several other classes to deal with like conditional branching, with arrow choice, arrow recovery, with arrow plus, fixed points with arrow loops, and so on. So how can you generally represent what is an arrow? So I'm giving here to you a notation which is not the most general possible, but it's an interesting way to build an arrow out of existing effects in Haskell. So there is a general way you can represent a good part of the arrows that may exist is by using this type. So this type will give rise to an arrow provided that f is an applicative functor, w is a comonad, and m is a monad. And if everything is an identity, then you just get a pure function out of it. So when you decompose that, you get three different data types, three different new types that do exist in various packages in the Haskell ecosystem. Kleisli, which is probably the most well-known, co-Kleisli, which is not often used, and Kaylee, which is not often used, but which will prove really useful. So I just included here comonads for the sake of completeness, but I will just drop them for now because we're only interested in applicative and monadic effects. So here is the simpler version of it. And this type is really what allows us to separate the configuration time effects, which are represented here by all the effects in this applicative layer, from the process time effects, which are represented by this M type, this monadic layer. And it really gives you the intuition to why it's easy to build or interpret effects into some existing arrows that will be made out of existing types, because monadic and applicative effects are aplenty in the Haskell ecosystem. So this is really relevant for code decomposition and reusability. So how do you build an arrow from binary effects? So I showed my rope type before, but in order to delve a bit more into the details, let me talk to you a bit more about what is a free arrow. So a free structure is anything that can give rise to a compositional structure given some data type of which we know basically nothing. So a free arrow creates an arrow out of some type that just has two type parameters, some type constructor that just has two type parameters. So what I represent here is the final encoding of a free arrow. So it's a name that may sound a bit barbaric if you're not used to that, but what it really means is that anything that you can convert into an arrow is itself an arrow. So by anything that you can convert, what I mean is that you have a function to convert that something, so something that I call f here. And so this f type, if I have what we call a natural transformation, so something that can transform any f of any inputs and outputs into some R type, which happens to be an arrow, then the whole of that is itself an arrow. You can write the instances there without placing any other constraints on f. This is why we call it a free structure. So I have my free arrow here, but okay, what if I need to do some I/O? For instance, my previously effects all deal with some I/O at some point, so in order to be able to handle these effects, my handler, which is this function here, will need to access some I/O. So I will need another version of free I/O for these effects, which constrains a bit more the R. And what about the other constraints that I defined before? Do I really need to develop one single new type for every possible combination of constraints? This is something I might not want to have to do. So a first change we might want to do is to drop that universal quantification. Like we will parameterize over this R type, over the destination type of the interpretation of our effects. And we can just as easily derive the instances for arrow choice, category, and every other control structure that we might want to apply on this free arrow like structure, provided that this R type, this target of the interpretation, provides it already. And again, without placing any other constraints on the F type, on our abstract representation of our effect. And so lifting our effects places no constraint on R itself. Even if R is now exposed, we can lift any effect in our free arrow-like structure without placing any other requirement on R. So it remains completely polymorphic. And so it will be the job of the handler, of course, to ask now which kind of constraints it would place on our core effect, on our target of our interpretation. So for instance, if I have a class arrow IO, which is just like monad IO but for arrows, then my handle console effect or my handle log effect or write file effect would take some effects and just call getLine or putLine on it, but of course to do that it needs to place a separate constraint. So lifting an effect does not place constraints on the target interpretation type, on the core, but interpreting it of course does. What now if I want to use multiple effects? I show you that the rope type can cope with multiple effects. If I have this free arrow like type, one thing I can do is just to use some sum type in order to have a disjunction of two different effect types. And then I can have one left effect, which I can lift like with that function, and a right effect, which I can lift with that one. And if I have some natural transformation for these two effects into my target type, then I can build an interpretation function for the sum of them into my target type. But of course, with more than two effects, we'd have sums of sums of sums of effect, which can become quite unwieldy. And this is why the rope type has made this transformation. So rope is just basically a free arrow, but with the following twists I presented. We parameterize over the target type, which we call the core, and we have an H list of handlers instead of just one. And instead of having one effect, we have a mantle of effects. So I mentioned that we want to benefit from the static structure of workflows. We want some information to be available at config time before any of the application logic runs. So it's important then to distinguish two ways to represent our abstract effects. And this will echo a bit to what I said before when I said that I prefer to use that form when I want to read files. So the difference between these two forms, the one when the file path is an input of the effect, and the one where the file path is a field of the GADT that is used to encode the abstract representation of the effect, is that the first one, the first representation, well, when I have that one, I know nothing beforehand about my effect. Before I actually interpret it, I don't know anything because no information is contained in that type. Whereas with the second one, my file path is accessible before I do anything with my interpreter function, before I perform any type of I/O. So this form of representing binary effects gives rise to more potent static analysis of the workflow and more potent config time computations. So a common, not say complaint, but a common remark that we've received about that work is that, okay, do we really need to use arrows for that? Couldn't we just do the same with applicative functors and monads? Well, first of all, even in the case where we do not have any monadic effects, it's not exactly the same. Let's say I have a type, let's say I represent my tasks with some type like that. I have some applicative functor f that's wrapping some computation A to B. Just configuration time effect, no load time, no process time effect. It will only do pure functions. So would we really need arrows in that case? Don't we have an equivalent for every arrow class in that way? Well, it turns out that with that type, if we just have a new type wrapping over that, we could implement all the interesting classes of the arrow stack class up to arrow choice. But the problem is that we would not have the right semantics with arrow choice, because the point of arrow choice is to be able to shortcut some effects with that, depending on the input of some task. And you can implement that, of course, with an applicative functor, but you would not be able to shortcut the effect. If you know a bit about the recent developments on applicative effects, you might know about selective applicative functors, but still they do not, they are not strictly speaking equivalent to arrow choice. So I will not delve too much into details here, but the branch function provided by applicative functors and the disjunction function provided by arrow choice do not exactly give rise to the exact same type. So it means that with an arrow choice you can always implement selective, but not the other way around. And finally, the final reason why we are not using applicative functions is that when you factor in I/O or any kind of monadic effects, then it sort of breaks the abstraction, because of course with applicative functions, if you represent your task that way, then you cannot lift I/O or impure function. It's not possible to convert that function type into that type. So to have the same n type, we would need to have this type to represent our task. We would need to force everything into I/O. And the problem is, if you do that, then the user is facing the underlying monad, so it breaks the abstraction. Whereas with arrows, well, both pure functions and effectful function can just be lifted into one type that remains opaque, and so the user is just presenting. So it provides a better abstraction, to our opinion. So in conclusion, the framework we presented here is based on existing Haskell applications, meaning that arrows are only used at the very top end. They're only used to really as an EDSL to structure pipelines. The rest of the functionalities can be implemented with regular applicative functors and monads. So it proposes separation of the capabilities, the features that we propose to the data scientists that will implement the pipelines. It separates these features from their implementation through abstract effects, giving us the possibility to swap the interpretation functions if you have, for instance, different deployment environments. It supports the separation between configuration time and process time, which means we can do some ahead of time analytics, configuration, and that we get some form of early failure. We can get some checks to be performed much sooner than they would be if we had just written some imperative code, because we have access to much more information and metadata about the tasks, which is something that does not exist in current industry-grade workflow tools like Luigi or Airflow in Python. And it promotes also extensibility and code reuse because it uses composable abstractions. Thanks to everybody. I'm now ready to answer your questions.